Okay, so welcome to the Learning from Humans session. So I know this is a robot learning conference, but in general, these robots should try to learn from various sources of data, and one of those very rich sources of data is humans, and how we can learn from various types of human feedback, and human data is definitely like an interesting research question, and we have 6 talks in this session. We're going to be kind of like addressing some of the questions in learning from humans. So our first talk is going to be co-presented by Laura Gracier, and we also have Saminda Agrawal, who is going to be online, and they're going to be co-presenting ICIM to Real reinforcement learning of robotic policies in tight human-robot interaction loops. All right, thank you.
Thank you very much. And we'll be presenting ICIM to Real, reinforcement learning of robotic policies in tight human-robot interaction loops. So in this work, we focus on the task of cooperative table tennis, where the goal for the policy is to maximize rally length with a human player. The video is showing an example of IS2R playing a long rally with a human. The video is in real time, and the policy is controlling the robot in joint space at 75 hertz. Policies can often sustain rallies of over 25 hits, and 340 hits is the longest we've observed, which is over 4 minutes of continuous play. We were motivated by a long-term goal of robot learning, which is to deploy robots in human-occupied settings. One promising approach for doing so is sim-to-real transfer. However, simulating human behaviors is difficult, especially when human behaviors change in response to a robot policy. Why is it difficult? Well, a human does not know what to do without a robot policy, and a robot policy does not know what to do without human data. Iterative sim-to-real, or IS2R for short, is a practical solution to this problem. IS2R bootstraps from a simple model of human behavior and alternates between training and simulation and deploying in the real world. We start by collecting an initial data set of human behavior without the robot doing anything. The initial data set is used to create an initial human behavior model, which in turn is used to train a policy in simulation. When the policy is converged, we transfer the weights to a physical robot. Initially, the policy can successfully return balls, but it struggles to sustain cooperative play. Then the policy is fine-tuned on the robot for a number of parameter updates. All human interaction data from fine-tuning is added to the existing human interaction data. The human behavior model is updated, and the policy is transferred back to the robot, back to simulation, where training continues using the latest human behavior model and the latest fine-tuned model from the real world. Then the policy is transferred back to the robot for another iteration of fine-tuning, and the process is repeated until the human behavior model converges. We use a new evolutionary strategy algorithm called black box gradient sensing to train our policies in simulation and the real world. It is interesting that BGS was the only method in initial experiments that transferred well to a physical robot. We also tried ARS, PPO, QT-opt, and SAC. The novel elite choice algorithm in BGS and orthogonal perturbations were key to success. One of our primary goals in this work is to simulate human player behaviors. How did we do that? Well, given a set of real-world ball trajectories, we estimate the initial ball position and velocity per trajectory, and then we derive ball distribution parameters from these values. Then in simulation, we represent humans as simple ball distributions and sample valid initial ball states from the distribution. The chart shows a few examples of real-world ball trajectories in green and the corresponding simulated ball trajectory in red. We evaluate IS2R by training 5 different policies, one each for 5 non-professional players of varying skill levels. We compare against a strong baseline sim-to-real plus fine-tuning approach, in which we train in simulation just once and then fine-tune on the real robot for the same amount of time as IS2R. Note that all of the policy evaluations were done blind, where the human did not know which policy they were evaluating. IS2R only achieves 9% longer rallies than the strong baseline on average. However, the median rally length for IS2R is 56% longer, and the 25th percentile rally length is twice as long. Additionally, the histogram of rally length shows that IS2R frequently achieves longer rallies more frequently, and all this together suggests that IS2R policies are more engaging to play with than the strong baseline. Saminda will now discuss more results.
Thank you, Laura. We further split players by their skill level, which were determined by using rally length statistics. For both beginners and intermediate players, IS2R significantly outperformed the strong baseline. The improvements differ between two groups, with IS2R yielding 70% for beginners and 175% for intermediate players. The policy trained by the advanced player has a different trend. Here, the strong baseline dramatically outperforms IS2R. We hypothesize that a good initial baseline model plays a large part in the strong performance, since the better transfer from simulation improves the efficiency of subsequent fine-tuning. Here we show a few IS2R examples for different players. The robot is ready in a forehand pose, and the human players play with the robot as naturally as possible. Player 1 is a beginner. Player 2 has a fast playing style. Both player and the robot ball trajectory are fast and low in height. Player 3 prefers to play high lobs. Each player has a different playing style, and policies have been converged to styles that are compatible for each player. We have also evaluated the impact of the human behavior model with respect to oracle ball distributions. These are the distribution if we had access to the final ball distribution for each players. We train model using oracle ball distribution in sim and fine-tuned in real. We have allocated 35% of the fine-tuning budget, which is equivalent to the IS2R final round of fine-tuning. As shown in the figure, the oracle model is as competitive as IS2R. This indicates that most of the benefits of IS2R is from iteratively improving the human behavior model. This suggests that if we had access to the final human behavior model, we just need to follow the strong baseline approach. The figure on the right shows a T-SNE projection of the ball distribution for a volunteer. It starts from a narrow distribution, and over time it grows to build a human behavior model. Policies learned using IS2R often generalized to new players in a zero-shot fashion. A player who was not involved in the training of the policy in any way can sustain a longer rally with IS2R learned policy. In comparison, policies learned using strong baseline alone are often brittle and are unable to sustain longer rallies. One of our future objectives is to use IS2R policies to develop an agent generalizes to any human player. Our approach has a set of failure modes. The video on the right side shows a few of them. This includes failures in hardware and vision. Hardware failures due to sensor measurement timeouts, and vision failures are due to false positive ball streams. This is contributed from our vision's large field of view, and there can be multiple balls at the same time. We have observed the following limitation in our approach. Our model doesn't handle out of ball distribution very well. For example, our human behavior model was not developed without spin, so we can't handle large amount of spin. Our method requires approximately 6 hours per player for IS2R and approximately 20 hours for the whole experiments. And we have only access to one hardware system. This is one of the reasons that we have limited our experiments and evaluation for 5 players. Finally, our method is subjected to sim-to-real gap. Thank you, and we are open for questions.
Right. Thank you. Any questions? Roberto?
Thanks for the talk. Did you try robot to robot? And if not, do you think the robot complements the human or is trying to learn to imitate it?
Yeah, this is a great question. So not yet, but it's a very natural question to ask. And I think you end up with so if a robot and a robot were playing together, I think it's not obvious, or at least it's not obvious to me, that the distribution would overlap with human plane distribution. So I think a really interesting open question is like, how could you leverage human robot-robot training and also anchor it to human-robot training distributions? And so I think there's a lot of work to be done around how big can you get these distributions, like such that do they overlap? Human and robot playing styles very different. I don't know, but it's interesting.
Oh, just to follow up on that. So it seems like the different playing styles, I'm wondering if that could be characterized by speed and amplitude. For example, there's sort of like you said that one player likes to play higher, slower ball. So, by folding up the table tennis, you can just play against yourself against the wall, right? And so it seems relatively easy to try that and have it learn to essentially adapt to those kind of standardized styles, and then to see how those play out against humans. In other words, it would quickly categorize the human into what their style was, and then index into that style it had self-taught.
It's so I think so to try and answer your question, I think how we started to make big progress here is this method for taking a set of human trajectories in the real world and then deriving a set of ball distribution parameters from those trajectories and then training against that. So in a way, what you've just described is what we try to do in simulation, which is instead of the real robot playing against a wall, it's playing against a ball distribution, which is a model of the human player behavior in simulation. This was kind of one of the primary goals of this work, which is if you can come up with that distribution and train in that in simulation and characterize it well enough, then you can get this transfer to a real world player. And I think what was interesting to us is we tried to define the sort of hand code up distributions in advance. And we did things that we thought were sensible. And then we would try that out, or we would try to train a model with that and then have the robot play the human, and it just didn't work at all. And so it was interesting that it's not obvious how to characterize distributions in advance, which is what led us to this iterative approach that you kind of bootstrap from this simple model and you just try and iteratively keep getting more and more data such that you can better characterize a player style.
All right, let's thank Laura and Samida one more time. Okay, our next speaker is Chen-Hao Lee, and he's going to be talking about learning agile skills via adversarial imitation of rough partial demonstrations.
My mouse. Yeah. Yeah. Can I have one of the microphones? I feel better. Hello, everyone can read. Great, yeah. So welcome. My name is Chen-Hao. I'm a master's student in robotics at ETH Zurich in Switzerland. And it's my great honor to present my work during my internship at the Max Planck Institute for Intelligent Systems in Germany with Marcus. So yeah, the title goes learning agile skills by adversarial imitation of rough partial demonstration. I'm going to talk about these concepts later. And maybe let me first give you some motivations. Well, as everyone knows that reward shaping is a very challenging task to do in reinforcement learning. And especially in robotics, if you want to really obtain some complex motion like backflip, it's really hard to design those terms. Then one alternative approach is through imitation learning. So where we train our learning agent to copy some behaviors from some experts. But the problem is you need these experts. So imagine if at the beginning we had nothing, it doesn't make perfect sense for us to first develop some other controllers and learn from these other controllers. So what we thought is, maybe can we simplify this expert acquisition process by maybe just hand-holding the robot and do the desired motion and learn from the induced trajectories. Generative adversarial imitation learning really provides us a way to do this without the need to synchronize the trajectories. Here, it trains a generative adversarial network, and the discriminator here is just trying to distinguish the motions from the agent and from expert. The output of the discriminator is converted to an imitation reward, RI, that is sent back to the training loop, the policy. But then it can be problematic in our case with handheld demonstrations because, well, handheld demonstrations are, in first place, rough. So rough really means there are certain state transitions that are not even physically consistent. For example, you can just hold the robot in the air for a long time, but of course, in reality, a robot would never float there. So this really results in a problem of strong discrimination where your discriminator is like identify, can quickly identify, well, this transition is from the robot, the other is from your handheld demonstration. And this is bad because it doesn't generate any change signal for the policy. And second, our handheld demonstrations are partial because when we handhold the robot, do this like trajectory, we don't actuate it at all because, well, it doesn't make sense to actuate. So we only have access to the base information. So then you don't have the, you don't have the possibility to do reference state initialization. We are forced to learn from scratch. Then to propose or to deal with these problems, we propose Wasserstein adversarial behavior imitation, or in short, WASAB. So let me guide you through this. There are some reference motion we want to learn from, continually base information handheld, and on the right is the typical RL loop. Then next, we just extract the corresponding information from the full state space, and then we send both to a discriminator. Discriminator is telling us how well we can learn from the demonstrations by giving us this imitation reward, RI. Now let's compare several different formulations of GAN. In the original GAN paper, the CE GAN or the cross entropy GAN really tries to predict the probability of certain transition from the policy. I forgot to mention that here in blue, I label the state transitions from the reference or the handheld demonstrations, and yellow, those from the policy. So CE GAN is predicting some probability, and people also propose to use LS GAN. But both methods really suffer from this saturation problem, especially in our case, because our handheld demonstration, as we said, it's rough. So immediately this discriminator just quickly get saturated. Immediately realize, this is something I cannot do. So it's really bad for the policy training stuff. Now, on the right, you can see this histogram. It's actually much worse. So here, this is the LS GAN reward, imitation reward distribution. Just, you can see a lot of information. Just the policy didn't see anything it can do to confuse the discriminator. So there's a high concentration on the 0 point. So to deal with this, we propose to use the Wasserstein GAN or W GAN. But here, instead of treating the discriminator as a regression problem or like predicting any probability, so we pose this question more in an unsurprised setting. So instead of, for example, anchoring your prediction of discriminator to +1, -1, as in the LS GAN case, we just say, oh, let the discriminator try to push this 2 as far as possible. So, which means to maximize the distance between its output when it's receiving transitions from different sources. So you have this distance, but it's kind of floating on the axis. And we really benefit this because now the strength of the discriminator is really relative. And there's no optimality here at all. So we don't have the saturation problem. And this really allows us to do, allows policy to maybe not completely invert this strongness or the strength of the discriminator, but maybe try to make the distance a bit smaller by doing something similar, a bit of a similar to the reference motion. And this is how we do the demonstration, and it's as easy as this. And we did 20 demonstrations for each motion. We have several tasks. And again, we use only rough and partial demonstrations. We train our policy in ISACGEM, and the learning of the desired motion backflip took only, I think, less than 2 hours. And for easier tasks, it's even less. And we deploy it back on the Solo 8 robot. And here's the slope. You can really see how the robot tries to stretch its legs while it's in the air to finish this backflip. And we believe this is the first learning-based flip. Correct me if I'm wrong. Now let's analyze it a bit. And here you see 2 heat maps. And on the left is the LS GAN case, on the right is our SLB. Here, the blue trajectory really denotes the demonstrated trajectory of the backflip. So they're the same here on both heat maps. But what is different is the color. The color means the inferred imitation reward. So on the left, you can see this color is rather uniform. It's not characteristic, but on the right-hand side, for Wasabi case, you can see clearly around the blue trajectories, there's a higher reward. So it clearly identifies, maybe I should go to these high reward area to obtain a higher imitation reward by doing something similar to the reference motion. Of course, we have some other tasks that looks similar, simpler. The first one is kind of hopping behavior. The second one is waving, but I would say their reward functions are not that trivial to design. And another very, huge advantage of our method is because we only use the base information, it doesn't necessarily restrict ourselves on certain robotic platforms. So what we did next is by using exactly the same recorded data from the solo robot, and we deploy Wasabi on animal. Looks a bit weird, but that's what the simulator gives us. Okay, limitations. I would say the largest limitation is because now even our reference motions are poor. We don't have a very good evaluation metric to pick the best policy. So you don't have anything to rely on now, really. So the best we can do is still to check the fidelity to the raw partial handheld demonstrations. You can use something like dynamic time warping, which allows us to compute a distance of two trajectories, even there are some time shifting of this trajectory. And there you can see how the points are matched. But there you need some distance metrics still, which is bad. And second, we really benefit a lot from the unbounded discriminant output. It really allows us to pick up maybe less the trivial change that we can make to train the policy. But when you have some other reward functions like regularization terms, it's a bit hard to balance the scales. Conclusion. Let's go back to our title, learning agile skills. Agile skills really means highly dynamic motions, very complex, that initially seem far away from or far away beyond the robot capacity. And we use Wasabi. Wasabi really allows us to employ this relative discriminant strength and can help us explore in a limited state space without the need of doing, it's not the need, but without the possibility of doing reference state installation. And finally allows us to do cross-platform imitation. So that's it. I hope you'll like it. Thank you very much, and feel free to ask questions.
All right, questions. There's a question up there.
Hello, really great work and really impressive results. One question I have is about the demo you give. So it seems like it's a position-based demonstration, like where you flip the base and you record the positions of the base over time. So I found that surprising because for the backflip, it seems like you need velocity information in the demo to get like that agile behavior. So I was wondering, did you like record the velocity information of the base, or did you just find that Wasabi was able to somehow recover that like high velocity behavior through just the positional demonstration? Thank you.
Yeah, thanks a lot for your question. Actually, we use you can see the markers of the Vicon system. We indeed use the Vicon system to track or to record the demonstration. That's why we didn't bring it here, because you need to bring like 10 cameras. Indeed, it's tracking the position, but we are not using it. So we use the position information to calculate the linear velocity, angular velocity of the base. And also there's something called a gravity vector, which is the projection of the gravity vector if you observe it in the robot frame. And lastly, for the flipping task, we also use the base height. So those are information we used. Yeah. So no exact position used.
There's a question up there.
Thank you for the presentation. I'm actually curious, when you are training it, how big is the variance of the data that you feed in the handheld demonstration?
Sorry, could you please repeat that?
So to my understanding, you say you use around 20 handheld demonstration. So I'm just curious, do you calculate like the variances between the different demonstration you provided?
We use this state transition. Maybe let me quickly go here. Yeah. So we have this discriminator, which samples state transitions from both the reference motion and the Rippler buffer generated by the policy. And what's different here in our work from the previous work is normally they use one single state transition, like just state and S prime. But here, because we use this relative strength of this discriminator, you can include as many as possible. So some tasks we use the horizon of 8. So you have 8 consecutive transitions. Those are not very doable in the previous case because the inclusion of more states will only make this discriminator even stronger. That's bad.
Okay, actually, that's not my
Oh.
question. So my question is more on, so you have 20 different demonstrations.
Yes.
How similar are these different demonstrations?
Sorry about that. We didn't do any, anything either to make the diversity higher or keep them like very similar to each other on purpose. So it's very arbitrary. And actually, I think from the work, I think it's better when you have some like slight variance there. You can be more robust.
Thank you.
Thank you very much.
All right, let's thank Chen Hao one more time. Our next speaker is Ryan Hoke, and he's going to be talking about Fleet Dagger, interactive robot fleet learning with scalable human supervision.
Any second now. Okay. Maybe. Of what? Oh, Flux. Huh. Why isn't this? Okay. This is hold on. I can do this. Don't worry. Thinks I have 2 monitors. Use slideshow. All right, there we go. We did it. Someone yesterday said we'll solve robotics before we solve AV. Okay, thank you, Dorsa. My name's Ryan Hawk. I'm from UC Berkeley, and I'll be talking about Fleet Dagger. So in the last few years, there's been a really exciting development in robotics. And it's that we've seen all these robot fleets are out there in the real world. Waymo, for example, has a fleet of over 700 cars operating in Arizona and San Francisco and soon Los Angeles. And other industrial deployments of robot fleets include applications like e-commerce, order fulfillment at Amazon and Ambi Robotics, and food delivery at Neuro. These robots use machine learning to achieve impressive generalization in a range of unstructured environments. But any data-driven approach usually runs into this problem of the long tail, right? There's always some new unseen scenario that the robots haven't seen before. So how do these companies ensure that the robot fleets can actually deliver the reliability that their consumers need? Well, one option is to fall back on humans. So if you had remote humans that are available, say, over the internet, they could take over control of these systems when these robot policy is not as reliable as you'd want it to be. This model is increasingly popular, and we see all these modern robotics companies like Waymo, Amazon, and Zoox using this model. But despite how much attention it's getting in the industry, we see comparatively little focus on it in academia. In academia, what we call this paradigm of ceding control to a human and learning from the human over time is interactive imitation learning. So here there's some switching policy we can call omega that decides whether the human's in control or the robot is in control at any given time. And in recent years, there's been a proliferation of these works that study interactive imitation learning, and primarily in the single robot, single human setting. And even in this single human, single robot setting, it's very much an open problem how to best choose this omega, because you often have these competing objectives of doing well at the task and reducing burden on the human supervisor. This is even less understood in when we generalize this to robot fleets with multiple humans, how do we do the supervisor allocation in this case? So to this end, we introduce a new paradigm we call interactive fleet learning, or IFL. And this is the first formalism for interactive learning with multiple humans and multiple robots. And in this paradigm, there's a pool of humans that are available, say, remotely over the internet, that can be allocated with some automated allocation policy, Omega, to the robots that need the most help in a large robot fleet. And these robots can severely outnumber the number of humans, and they're also continually learning from human experience that is added over time. And they share policy pi theta t. Now, more formally, we can model these as n individual robots and Markov decision processes that are identical apart from the initial state distribution. And we can turn this into one big MDP with vectorized states and actions. And what we care to find is this allocation policy Omega, which is a mapping from the state of all the robots in our fleet and their shared policy pi theta t to a binary assignment matrix that indicates which human is assigned to which robot at a given time. Now, this allocation affects the policy learning, which affects the allocation, and you can see how this can get complicated. And the objective that we care about, the IFL objective that we want to optimize, is this new metric we call the return on human effort, or ROHE. And intuitively, you can think of this as a measure of the performance of your robot fleet, normalized by how much human effort it took to get to that level of performance. Now, of course, this IFL is just a model, and all models have assumptions. So some of the assumptions that we make are that the humans are homogeneous, that all the humans demonstrate in the same way, and also that all the robots are independent. So this is not a robot swarm. There's a large body of work on robot swarms, which are typically a large number of low-cost robots operating in a shared environment toward a common objective. Here, we assume the robots have their own independent environments. So you could think bin on an assembly line, for example. Now, we don't actually know which Omega is the best. So to this end, we propose this IFL benchmark. And this is also the first benchmark that's specifically for interactive learning, even for single robot, single human algorithms. And I'm happy to say that as of today, it's open to everyone. It's an open source Python toolkit, freely available on GitHub, easy to use. And we hope that it will make it easy to develop IFL algorithms and also evaluate them in a standardized way. And in order to simulate these large fleets of 100 or even 1,000 robots on a single GPU faster than real time, we built on NVIDIA Isaac Gym, which was released last year for end-to-end GPU acceleration. As for the actual algorithms that we implement in this benchmark, an IFL algorithm just specifies one of these Omega allocations. We propose a family of algorithms called Fleet Dagger, or you could think of it as a meta algorithm that outputs algorithms, where it takes this priority function p hat as input, and it outputs an Omega. This priority function is an individual mapping from one state and the policy to a scalar value. And this is used by each robot autonomously to score itself, and Fleet Dagger turns that into an allocation. Now, of course, there are other ways that you could do IFL allocation, so that's why Omega, the broad space, is not fully covered by the output of Fleet Dagger, but it covers quite a big space. And the policy learning is done with Dagger, as you may have guessed from the name, but you could theoretically use any other learning algorithm like policy gradients or other reinforcement learning algorithms. So particular instantiations of these Fleet Dagger algorithms include these 5 that we implement and study in this work. So this includes allocations like constraint, uncertainty, risk, and also, surprisingly, includes fleet versions of existing single robot, single human interactive learning algorithms like Ensemble Dagger and Thrifty Dagger, which shows that by choosing appropriate choice of p hats, we can also cover a lot of the related works that already exist. So we ran simulation experiments with a fleet of 100 robots in simulation and 10 algorithmic humans. And we had these 4 metrics, and we found that 1, the allocation does have a significant impact on the performance of the fleet. And we found that this novel CUR scheme achieved higher task throughput than the baselines on average, as well as lower hard failures and idle time on average, notably not in the Allegro hand, and higher return on human effort. And this increasing return on human effort over time also indicates that the robots learn when to stop asking for help because it is a ratio. And of course, we also did physical experiments. So we are an academic lab, so I had to be a bit creative about how to get a fleet of robots. So what we did is we repurposed 2 ABB Yumi robots in 2 different physical labs about 1 kilometer apart into 4 individual robot arms. And we had 2 humans connect here remotely over the internet to do teleoperation. And the task was an image-based block pushing task that was reset free, in that as soon as you reach the goal, which was programmatically generated in the image, it can sample a new goal. And we observed similar trends in these results here, albeit more variance due to real results. Now, in future work, we want to do several things. We want to lift assumptions. There's some papers in this conference that will help us do so. And we want to study interactive reinforcement learning and do more large-scale physical experiments. But since this is such an unexplored area, there's no dearth of interesting subproblems to explore. And I'd like to conclude by arguing that this idea of interactive fleet learning, it isn't just increasingly relevant, but it's also inevitable, because these robot fleets are here to stay and they're only going to get larger. So this paper is really about providing a toolbox for IFL with algorithms, benchmarks, and formalisms that hopefully may facilitate any of you and ideally power the robot fleets of the future. Thank you very much for your attention.
Okay. Questions for Ryan? So quick question. You mentioned the fact that the assumption that humans are homogeneous, and they're very much not homogeneous.
Yeah.
So how do you think about like extending some of the like algorithms like in the fleet dagger that you discussed in terms of like capturing the fact that humans are pretty heterogeneous?
Yeah, that's a great question. And actually, Dorsa has a paper in this reference at this conference. It's a plug there for multi-human imitation learning. So I think, so humans are noisy, obviously, and that's maybe the biggest problem with imitation learning, and maybe interactive fleet learning even more so because there's multiple humans. So the main problem is that they're multimodal and suboptimal. So one next step is to make algorithms that are robust to this. So you could consider extending things like implicit models, like implicit behavioral cloning. There are transformer models like that, like perceiver actor, which are able to capture multimodality. So I think it's very much still an open problem, but there's a lot of progress that is being made in parallel there that we can fold into these kind of policies.
Thank you. Can you elaborate a little bit more on how the robots scored themselves so they know that they need teleoperation?
Yeah, right. Yeah, I kind of glossed over that for time, but the idea is that so there's 2 ways you can think of interactive learning. There's human-gated mode, where the humans are supervising, constantly monitoring the robots, and then they say, oh, it's time to intervene. Or you could put that burden on the robot, and the robot says, I need to actively request for help. And that's really the only way that you can scale to a bunch of human or a bunch of robots per human. So you could think of various quantities. So for constraint uncertainty risk, the uncertainty is like ensemble variance. So at a particular state, if your policy has like 5 different neural networks that are bootstrapped on different subsets of the training data, then you can measure their disagreement, and that can be a proxy for maybe I need help. And there are other quantities you could consider.
Yeah, thank you. So let's thank our speaker again. Our next speaker is Shanshu Lee, and he will be presenting Behavior 1K, a benchmark for embodied AI with 1,000 everyday activities and realistic simulation.
Sorry, still setting up. One sec. Okay, apologies for the slow setup. All right, hello everyone. My name is Chengshu Eric Lee from Stanford Vision and Learning Lab. I'm very excited to share with you Behavior 1K, a benchmark for embodied AI with 1,000 everyday activities and realistic simulation. First, let's imagine that there's a robot that can do housework for you. What would you like it to help you with? Cleaning the kitchen floor, shoveling the snow, folding laundry, cooking breakfast, buying shoes, opening Christmas gifts, or maybe cleaning after a wild party like this. While for many existing robotics benchmarks today, the tasks are usually handcrafted or selected by researchers themselves, we decided to adopt a more human-centered approach to activity selection in behavior. Concretely, we sourced 2,000 plus candidate activities from time use surveys and WikiHow articles. Then we conducted a large-scale online survey with a total of over 1,400 participants, asking people how much they want a robot to do the activity for them on a 10-point Likert scale. Our survey covers a wide range of demographics within the US population from various age groups and socioeconomic background. The survey results shows that the humans want robots to perform a very wide range of activities for them. Tedious tasks like cleaning score the highest, while recreational tasks like gameplay score the lowest. We showcase 2 of the top 10 activities instantiated in our simulator on the right-hand side. Based on the survey results, we include the top 1,000 activities in our benchmark, and these activities are deeply grounded on actual human needs, goals, and values. Before we can concretely define these 1,000 activities, however, we need to first figure out what objects and object properties are relevant for each activities. Without narrowing down the scope, our activity annotators can easily be overwhelmed. To do that, we first source 5,000 how-to articles and videos online to figure out what objects are needed for each activity. With annotations from crowdsourced workers and GPT-3, we then built a large-scale common sense knowledge base of object properties, such as what objects are cookable, deformable, and so on, and transition rules such as cooking recipes. To finally define the activities, we adopt BDDL, a symbolic domain definition language from our prior work, Behavior 100. It is accessible and easy to use for lay people, but flexible and powerful enough to capture rich semantics. Each definition describes the initial and goal condition of the activity in predicate logic. Now that we have all the activities defined in the symbolic space, we need to acquire actual 3D models to instantiate these activities in any 3D simulation environment. With the goal of training generalizable agents, behaviors places a very strong emphasis on ecological and diverse scenes and objects. We provide 50 high-quality, fully interactive scenes across 8 different scene types, including houses, hotels, restaurants, grocery stores, and so on. To cover the diversity of our 1,000 activities, we also curated a data set of over 1,200 object categories and over 5,000 object models. Each object model is annotated with rich semantic annotation like mentioned before, and also physical properties such as articulation, mass, friction, and so on. These annotations ensure that the interaction with the object is realistic. As many of us know, embodied AI research has greatly benefited from simulation environments because it's usually faster, safer, and more reproducible to iterate algorithms in them. The question is, how do we simulate these 1,000 diverse activities with various object properties and states? The complexity of Behavior 1K is beyond the capability of any existing 3D simulator. As a result, we will need to build our own. We present a novel simulation environment, Omni-Gibson, that provides the necessary functionalities to support and instantiate Behavior 1K. Omni-Gibson is built on top of NVIDIA's Omniverse and PhysX5, providing realistic rendering and physics simulation of not only rigid bodies, but also thermal effects, complex state transitions, lighting and reflections, fluids, deformables, and transparent objects. OmniGibson can also generate highly realistic ray trace and path trace virtual images. In our Amazon Mechanical Turk studies, OmniGibson scores the highest in terms of photorealism among 5 simulation environments with a significant margin. Most importantly, OmniGibson supports realistic robot interaction with objects, including manipulation of rigid bodies, deformable objects, and fluids. These aforementioned features really set OmniGibson apart from existing simulation environment in terms of realism. So how do today's robot learning algorithm do on behavior? We benchmark on 3 representative activities that involve pick and place of rigid bodies, manipulation of articulated objects, and interaction with cloth and fluids. For instance, in a cleaning table task, the agent needs to grasp a soft towel, dip it into the water, and then wipe a table clean. Now let's take a brief look at the results. Each row is a baseline, and then each column is a task. The first takeaway is that vanilla RL with the low-level action space using SAC completely fails to learn because our activities are very long horizon, have sparse reward, and require many different types of skills. The second takeaway is that the model with action primitives achieves better success by leveraging privileged information and also temporally extended action space. This finding hints on the importance of learning diverse skills in order to solve tasks in behavior. The third takeaway is that memory brings in extra improvements for success rate across the board, especially for longer horizon tasks. At last, we ask, what are some of the main sources of sim-to-real gap in Behavior 1K? We built a mock-up apartment at Stanford and converted it into a virtual interactive scene in OmniGibson. From these 2 images, you can see the visuals are quite similar. We trained the action primitive-based policy mentioned before in simulation and directly deployed it in the real world. Thanks to our very realistic simulator, zero-shot sim-to-real transfer achieves some partial success in the real world, despite differences in the 3D models and sensor signals. For more analysis about the sim-to-real transfer, please stop by our poster. Our work is obviously not without limitations, and we're actively working on addressing these issues. First, we are in the progress of running a much larger scale and more representative human preference survey to avoid any potential biases or noise. Secondly, our backend Omniverse is extremely powerful, but also expensive. It requires at least a GeForce RTX 2080 series card. Thirdly, simulation speed of OmniGibson can be further optimized, especially when fluids and deformables are present. We're actively working on this as we speak. Last but not the least, more in-depth sim-to-real experiments and analysis are needed to gain insight into the potential of behavior for real-world robotics. And we'd like to invite the community's help on this. I'd like to acknowledge all the wonderful co-authors and team members of Behavior, as well as the funding sources. In conclusion, we present Behavior 1K, a benchmark for 1,000 everyday household activities. Our benchmark is human-centered, it is diverse, and it is realistic. And we hope it can serve as a useful platform for robot learning researchers. In fact, we have just beta released our platform. Please visit our website to try it out. Thank you.
Thank you. Is there any question?
Can you elaborate a little bit more on the sim-to-real experiments that you have done and what type of failures you see? Like what are kind of the limitations on the sim-to-real side of things? And have you guys thought about real to sim, like incorporating that into your current system?
Yeah, absolutely. I think there are multiple levels. So essentially, we did a pilot study of sim-to-real. It's not like super complex. What we find is that there are sim-to-real gap in both the visuals and actuations. So for visuals, sometimes it comes from the rendering of the exact camera parameters are slightly different. The exact 3D models are slightly different. For example, each wooden table have its unique texture. It's hard to exactly match them. And actuation noise also matters because grasping a small object is a very fine-grained manipulation task, and sometimes the real robot just doesn't do the things that you command it to do. I do think real to sim is a good way to have this sandbox environment to test sim to real though, because then you are only testing generalization across the same scene instead of generalization across novel objects or scenes. So I think it's a good debugging tools, and I think it's not too difficult. Each lab have moderate resource can all do that, and we'd love to invite the community's help on this.
So can I ask, are these tasks parameterized in the sense that cleaning up after a wild party sort of depends on how wild the party is.
Right. Essentially, we also adopt more like a crowdsourced approach. We essentially have a short prompt for our annotators, and it's up to them essentially to define what they have in mind in terms of a wild party. So usually speaking, for a wild party, they will include a lot of objects that are misplaced, or fluids being thrown on the water, throw on the table that you need to clean up. So yeah, so we don't want to command that ourselves. We ask the humans to do that.
So we have time for one more question.
There's a question from online. So the question is, what task, interactions, or material did you consider adding to the benchmark, but found it difficult, such as because of difficulty of modeling or simulation challenges?
So is the question about what kind of task object states are in the benchmark and what are some of the difficult parts to simulate?
So it's difficulty of modeling or simulation challenges.
I think the question was there any task that wasn't included because it was too hard to simulate?
Right. Yes, we definitely do a bit of filtering. I think there are extremely fine-grained manipulations, such as screwing something inside a cork. I think recently there's an NVIDIA paper called Factory about this. I don't think we have tasks that as fine-grained as those. And also, I think for tasks that involves modeling of other agents, like modeling another human or another live animal, that's, I think, also an open research area that we hope to wait until the field to be more mature before we can incorporate this into our benchmark.
Okay, thank you. Let's thank our speaker again.
Thank you.
So the next paper is Watch and Match, Supercharged Imitation with Regularized Optimal Transport. And it will be presented by Sithan Haldar.
So hi, I'm Siddhant, and I'll be presenting our work titled Watch and Match, Supercharging Imitation with Regularized Optimal Transport. There's joint work done with Vaibhav Mathur, Dennis Yaratz, and Laurel Pinto at New York University. So in recent years, we've seen some really cool tasks being done by robots, like solving a Rubik's Cube, doing parkour. And a year ago, when I started my PhD, watching these videos made it seem like robotics is either solved or close to being solved. However, a closer look into these systems reveals that you need to invest a lot of time and effort to make these work on these really narrow scenarios. Imagine you want to teach your robot to do one of these tasks. I'm sure none of us would want to spend a lot of time in order to teach these skills to a robot only to have it go to waste the moment you change the scenario in which you're operating. So in this work, we our goal is to minimize the time and effort required to teach these skills to a robot. So how should we teach our robots? A common way of teaching something to someone is through imitation. And imitation rests on the principle of watch and match. Watch what someone else is doing and match their actions. A popular method for imitation learning is behavior cloning. Here, an expert makes the robot interact in an environment to get some demonstrations, and you learn a policy on these demonstrations using supervised learning. However, though these approaches seem to work pretty well, they tend to require large amounts of data, which in turn needs a long time to collect. And since we want to minimize the amount of time required to teach these skills, let's look at what happens when you do behavior cloning on small data sets. Consider the task of opening a box. Here we provide a single expert demonstration with a joystick and train a behavior cloning policy on this. We observe that when starting from the same initialization as the demonstration, you succeed in completing the behavior cloning succeeds at completing the task. However, if the initialization deviates even by a little amount, the policy struggles, and this is a common problem known in behavior cloning referred to as the distributional mismatch problem. So a fix for this is that you can just do online learning to fine-tune this policy and try to make it work on your whatever task you're performing. So given an expert and agent trajectory, we use an encoder to obtain a trajectory of encodings. Now, this use of an encoder is necessary because directly learning policies on these high dimensional visual spaces is difficult. And so we encode them to a lower dimensional representation. And now, given these trajectory of encodings, we want to calculate, get a measure of similarity between them. And we use trajectory matching schemes for this. So there can be multiple variants for this. One is that you can just match each time step to each time step. And the problem here is your metric becomes constrained in time. Another method is something approaches like Gale use, which is just learn a discriminator to classify whether your trajectory belongs to the agent or an expert and use that as a reward. But the issue here is that you need to learn this discriminator or the reward function, and that makes it very sample inefficient. So in our work, we use optimal transport. And the good thing about optimal transport is you can do away with learning a completely new reward function. To know more about optimal transport, please, you can refer to our paper. But yeah, so given this optimal transport-based matching scheme, now you can obtain a matching score, which is which denotes how similar the two trajectories are. And you can use this as a reward to do online learning to fine-tune your behavior policy. Now, though this pre-training plus fine-tuning approach seems reasonable, it does not work very well. And the issue is that just naively combining offline pre-training with online fine-tuning struggles to perform well. And let's understand this through a toy example. Consider the task of reaching the green square at the bottom right from the red, orange square at the top left. We give a single expert demonstration here and train a BC policy on top of this. As you can see, the BC policy quickly deviates from the expert trajectory and then fails to complete the task. We fine-tune this policy using the online learning scheme just described, and this suffers from the same problem of deviating from the trajectory, failing to recover, and hence failing to perform the task. And this is something that's been studied in previous literature, and you can refer to these papers to know why this happens. But in order to solve this problem, we propose an algorithm regularized optimal transport, where we do online fine-tuning with BC regularization. So our objective function for the online learning part consists of a RL loss, which is a Q-learning based loss commonly used in off-policy RL. We add a BC regularization term to it, which is supposed to keep the policy close to the expert data distribution and just keep it close to it. And the caveat here is if you're always applying regularization while training, your policy might become biased towards the expert data, and that is undesirable. So we add an adaptive weight lambda in order to control the amount of regularization applied at different stages of online training. So this is our simplified loss function. And the idea is keep your online policy close to the behavior policy when the behavior policy shows better performance. Now, in order to compute the adaptive weight lambda, we use the current equation. And basically, lambda just represents the proportion of states from your sampled states where the behavior cloning policy shows better performance than the current policy. And the idea, again, is to increase the amount of regularization when your behavior policy shows better performance. So let's go back to our toy experiment. Applying ROT to this scenario, we see that the policy quickly recovers, sticks to the expert demonstration, and is able to complete the task. Now, and interestingly, now we can start from random initializations unseen in the expert demonstration and still complete the task. And let's look back at the task of opening the box. Like behavior cloning, ROT succeeds in completing the task from the same initialization. However, ROT now can also perform the task from any random initialization in front of the box. So putting it all together, we start with collecting a single expert demonstration. We initialize a behavior policy using behavior cloning. We fine-tune this behavior policy online with ROT, and we continue this online fine-tuning for an hour to obtain a policy which generalizes to unseen initializations. We evaluate our approach on 3 environment suites: DM control, OpenAI robotics, and the MetaWorld benchmark. These are our results, and we observe 7.8 times faster imitation as compared to prior work. We evaluate our approach on a set of 14 real-world tasks, and for these tasks, these high-dimensional images are given as an input to the policy, and the policy is supposed to spurt out the end effector positions. For each task, we give just a single expert demonstration and only allow 1 hour of online fine-tuning. These are our results. And as you can see, ROT significantly outperforms behavior cloning and prior adversarial IRL-based approaches. Now, our work has some limitations. One is that we assume that we have expert demonstrations. And the reason for this is like, since the demonstrations are the only signal being given to the policy here, suboptimal demonstrations result in suboptimal actions in this scenario. Another problem is that our model struggles when the task features aren't visually distinct. And let's understand this through an example. Consider the task of placing the peg in a cup. This is an expert demonstration where the robot arm places the peg inside the cup. And this is a failure mode from a learned policy where the peg is placed behind the cup. And as you can see from these two frames look pretty similar, and it's difficult for the model to tell them apart. However, it must be noted that in our work, we train all the policies are trained from scratch, and maybe using some pre-training approach for on the representation learning side can help alleviate this issue. So this is our work, regularized optimal transport. Some key takeaways are that we learn from high dimensional images. We learn in a single hour and from a single expert demonstration. Our video and open source code are available at this link. And apart from what's been shown, ROT also works on state-based settings as well as task-specific environment rewards. So thank you.
So we have time for one question.
My first question is, where are all the assigned respondents when we're asking for questions? But all right, great work. I'm curious about, can you say a few words about the computation demands of computing optimal transport?
Like the computation as in time compute.
Time complexity. I mean, as an optimal transport known to be extremely difficult to.
Oh, yeah. But so the thing is, these projects, so for simple skills like this, you don't need a lot of time steps, like 30, 40 is enough usually. And when you have that smaller time step, you can get a cost matrix pretty efficiently, just put it on the GPU, compute your distances. So you have a cost matrix, you have two distributions, which is like 40, 50 steps at most. And that doesn't take much time. So it's like very small compared to the total pipeline.
So it's actually not the optimal transport, it's an approximation.
So this is the regularized one, which adds an entropy regularization, and then that makes it quicker. And you can
Okay.
Let's thank our speaker again. So this is our last paper, temporal logic imitation, learning plan satisficing motion policies from demonstrations, and it will be presented by Yanwei Wang.
Okay, hello everyone. My name is Yanwei. I'm presenting temporal logic imitation, learning from plan satisficing motion policies from demonstrations. This is joint work with Nadia Figueroa, Shen Li, Anki Shah, and Julie Shah. So we've seen a lot of work in this conference that focus on generalization to different tasks or different objects. Here, we study the generalization to out of distribution states for imitation learning, especially when there are a lot of perturbations. Consider the task of scooping. Given the single demonstration, we want to be able to learn reactive motion policies, such that given a perturbation, the robot is able to react at a motion level. However, if the perturbation is too big and that leads to task level failures, such as dropping all the marbles, the robot is not able to replan. And consequently, the motion imitation is successful, but the task fails. This highlights the challenge of using motion imitation to replay tasks with temporal and spatial constraints when there are perturbations. These methods are at best ensure goal reaching or recover at a motion level to stay close to the demonstration, as we've seen just now. We think we're proposing imitating with a discrete plan instead, where the continuous motion is successful because it traces out a discrete plan of mode sequence that's implicit in the demonstration. For example, here, the demonstration the policy rollout goes through a reaching mode, a scooping mode, and a transporting mode. The scooping mode has a mode boundary that ensures contact during scooping, and transporting mode has a mode boundary that ensures the spoon is level without spilling. Anything else can be in a reaching mode. And a policy rollout is successful as long as it goes through these mode sequence. And no matter how different it is from the demonstration after perturbation, it will be successful. Applying this view, it's easy to see why prior approach fails, because even the policy recovers at the motion level, it introduces an invalid mode transition as it tries to directly go from the reaching mode to the transporting mode, shown by the red cross. In contrast, if we're imitating with respect to a discrete plan, then the system is able to replan at the task level, so that ensures all the mode transitions are valid. The ability to replan on the fly after sensor detecting a undesirable mode transition comes from a linear temporal logic formula we query from the humans. Let's now formally introduce the problem, temporal logic imitation, where given sensors that detect modes, successful demonstrations of reaching a goal, and temporal logic formula specifies valid mode transitions, we want to be able to learn continuous policies that can simulate any discrete plan given by the LTL under arbitrary perturbations. A naive way to solve this problem is just learn motion policy for each mode and then sequence them together through LTL. However, we don't know the precise mode boundary in this imitation setting. Therefore, if a state is out of distribution, it can lead to future invariance failure of leaving the mode prematurely. Even the LTL is able to recover, the system might enter the mode at a state that will actually cause the same mistake down the road. Therefore, it might get stuck in this loop at a task level. What this means is not every discrete plan is realizable by the low-level motion policy that are generically learned from data. We need to ensure some properties when we're learning these policies. It turns out we need to ensure two properties, goal reachability and mode invariance of the motion policy. What is goal reachability? Let's consider this task of learning from these two demonstrations in thick line of reaching this orange circle. If we use behavior cloning and then plot the policy rollouts in streamlines, we see all of the blue trajectories reach the goal successfully. And the red trajectories, actually, they never reach the goal. They get stuck in the spurious attractor because they're out of distribution. If we apply dynamical system on the same data, which was actually introduced by Professor Biller this morning in the keynote session, we see that all of the trajectories are guaranteed to reach the goal. However, the red trajectories, they leave the mode before coming back, thus failing the task. Therefore, we also need to ensure mode invariance to make sure all of the flows starting in the mode stay in the mode before reaching the goal, until reaching the goal. How do we ensure that? First, we need to estimate the unknown mode boundary. And then when the system experiences a failure, we can put a cutting plane at the failure on the boundary that separates the failure from all the valid in mode states. This way, we can build better and better mode boundary estimation through more and more failures. We treat these cutting planes as collision objects that can trap the flow inside. We call this a modulation strategy. We show a dynamical system plus modulation, and we're able to ensure both goal reachability and mode invariance. If we apply the same modulation strategy to behavior cloning, however, we can only ensure mode invariance. And this plot actually shows that low-level motion policies can be classified into 4 classes, depending on whether it has the invariance property or the reachability property. And in our work, we show only when a motion policy has both invariance and reachability property can we prove it's able to carry out any high-level discrete plan. Let's see some actions. We learn dynamical system, and if we perturb it to a state that's out of distribution, it will lead to a future state that drops all the marbles. If we have LTL, the system's able to replan and rescoop. However, without modulation, if you perturb it to the same out of distribution state, it will repeat a mistake. With modulation, the system will first experience the failure and quickly learn to update the low-level policy so that when you perturb it to give it the same perturbation, it won't make the same mistakes. And this is the key here. Now let's test our system's generalization capability to different perturbations from unbiased humans. And let's just focus on one case here. After dropping the marbles, the system is able to sort of re-scoop. And the nice part is, if we're imitating a discrete plan, the plan will never go through the transporting mode until the scooping mode has been properly gone through. And this strategy allows us to ensure all of the experiments we run are successful 100% without any cherry picking. And what's cool is there are actually patterns coming from this unbiased humans we just randomly recruited. While you might think most of the perturbations should be adversarial, actually there are also cooperative perturbations where the humans are trying to help the robot. And in this case, having a dynamical system as a compliant policy really ensures smooth human-robot interaction. Finally, the contributions. We formally proposed a novel problem setting called temporal logic imitation that guarantees task success given arbitrary perturbations. And then we show motion policies needs to have both reachability and invariance properties in order to satisfy any high-level discrete plan. And lastly, our modulation strategy gives this invariance property to reactive motion policies that are learned with only 1 to 2 demonstrations. We have more experiments run showing the reactivity of our system, and we welcome you to check out our website. And the limitations. First, we assume modes, the temporal logic formula and perfect sensors are either defined or given in this work. And then the modes are assumed to be convex so that we can approximate the boundary, and that really limit the imitation in the task space rather than a joint space. And lastly, the state space policy we propose here generalizes to out of distribution states or any perturbations, but it does not generalize to visual inputs, which will be future work. With that, I thank you for your attention. Thanks.
So we have time for just one question.
Thanks a lot for the very nice presentation. You showed a nice animation on how you introduced the additional boundaries, but I didn't totally get how that works. Like the position is okay, but the orientation is not. So you only put the additional constraint on the orientation, and how is that decided?
Yeah, that's a great question. So we run like a quadratic program to find the orientation of the boundary where it separates the attractor, or the prior visited in mode states from the failure modes. So yeah, we do have those constraints to make sure it doesn't cut out regions unnecessarily. Yeah.
Thank you so much. Let's thank our speaker again.